In this video, we'll discuss the QR factorization. The problem is to find Q and R for the QR factorization of the following matrix. What we want to do here is to write the matrix A as a product, Q times R, where Q is an orthogonal matrix, meaning it has orthonormal columns, and R is an upper triangular matrix. Now this will be possible whenever the columns of A are linearly independent. So our first step will be to take the columns of A and turn them into an orthonormal set. And we can do that using the Gram-Schmidt process. Now in our previous video on the Gram-Schmidt process, we started off with this same set of three vectors here, and we found the following orthogonal set. So I'm going to write here, previous video. If you don't remember this example, you can look back at that video on the Gram-Schmidt process and figure out how we built this set X. We also mentioned in that video that we may want to simplify this last vector here. We could actually scale that by dividing each component through by 2. I think we should do that here just to keep the numbers a little bit simpler. So this last vector is going to become 4, -2, -3, -3. So at this point we have turned the columns of A into an orthogonal set. But what we really want is an orthonormal set. So we're going to have to go through, divide each of these vectors, each of these three vectors, by its length. So the length of that first vector is the square root of the sum of the components squared. So we'd have 1 squared plus -1 squared plus 1 squared plus 1 squared. That gives us root 4, or in other words 2. So to normalize that vector, we're going to go through and divide each of those components there through by 2. So this is what our orthonormal set is going to look like. That first vector will be divided through by 2. And in a similar way, we can calculate the length of this second vector here to be root 76. So the normalized version of this vector will look like this. And if we look at the simplified version of this third vector here, its length is root 38. So the normalized version of that vector will look like this. I'm not going to worry at this point about rationalizing any of these fractions or simplifying these fractions. We'll do that at the very end of the problem. At this point, we're able to write down our matrix Q. So the columns of Q will just consist of these vectors here that form our orthonormal set. Now let's figure out how to calculate R. Remember that we want A equal to QR. So the trick here will be to multiply on the left by Q transpose. The reason that we do that is that Q is an orthogonal matrix, so Q transpose Q is guaranteed to equal the identity matrix. So in other words, on the right side we've got IR, which just gives us the matrix R. So we've got this little formula here that reminds us how to calculate R. I think I'll circle the rows of Q transpose here and the columns of A just to make this calculation go a little bit more smoothly, because there are a lot of roots in this expression. So the nice thing about this calculation is that when we grab the first row here, everything's over 2, so we really just need to pay attention to the numerator here. We're getting 1 times 1 plus minus 1 squared plus 1 squared plus 1 squared gives us 4, so it's really 4 over 2. Moving over to the second entry, again, if we just look at the numerators, 1 times 2 plus minus 1 times 1 plus 1 times 1 plus 1 times 1, that's going to give us 3, so that's 3 over 2. And then finally in the top right here, we've got 4 over 2. So we'll simplify these expressions, or these entries, in a minute. Moving into the second row, we've got 0 over root 76. Then we've got 19 over root 76. And for the third entry, 24 over root 76. Okay, now moving into the bottom row, we've got 0, 0, and then finally 4 over root 38. Now that we found Q and R, let's think about simplifying the entries in these matrices. Top row comes out to 2 3/2, 2. In the middle row, if we simplify this fraction here, 19 over root 76, we can call that root 19 over 2. And in this third entry here, this guy's going to simplify to 12 root 19 over 19. And then finally in the bottom row here, 4 over root 38 is going to simplify to 2 root 38 over 19. So I think I'll label this clearly as R and just highlight that. That's 1/2 of our final answer. And very last thing we'll need to do is just simplify our matrix Q. So we can refer back to the matrix Q that we had written down earlier in the problem, and we now just need to simplify this for our final answer. First column looks fine as is. Second column, we're going to rationalize these fractions to get (5 root 19 over 38, 7 root 19 over 38, and then finally root 19 over 38 for those last two entries. For our last column, again rationalizing, we'll have 2 root 38 over 19 minus root 38 over 19, and then negative 3 root 38 over 38 for our last two entries. And there we have the simplified version of Q. So there we have our final answer. We've found Q and R from the QR factorization, and we've also done the extra work of simplifying both of those matrices at the end of the problem.